So, in our previous two sessions, we had learnt about the EM algorithm and we had seen an application of EM algorithm in R. In this session, we would be seeing the properties or advantages of using a EM algorithm. By now, we know that EM algorithm is a general multipurpose algorithm that can be used for finding maximum likelihood estimates in context to data sets which contain missing data. And this missing data can be the random effects also, or this missing data can be the latent variable also. So, in general it encompasses a very broad area where missing data come in a lot of forms. Specifically in this session, we shall be seeing what is the advantage of using the EM algorithm, what are the properties of EM algorithm, and why EM algorithm is popular. In the next session, we shall see another application of EM algorithm, but this time on a real life data where we would be estimating the parameters of a mixture distribution. But in general, the EM, because of the fact that the log likelihood increases for EM at each iteration till convergence and we do not need to compute the second derivative, EM is a preferred method. The objective of this session is to know about the properties of EM algorithm. We start with the advantage of EM algorithm. The first advantage is that for a EM algorithm, the log likelihood increases at each iteration till convergence, and although the computations are tedious, they are straightforward. And the fact that they are tedious does not really matter, because once they are implemented, the program does the repetition, the computer does the iterations, and so this does not need to be done by hand. Finally, EM algorithm does not require second derivatives. Now, there are other optimizers like the Fisher scoring algorithm, which needs computation of the second derivative. Having said that, we just want to point out that there are certain disadvantages of EM algorithm also. It is not that EM is absolutely free of disadvantage, and the first disadvantage is that the EM may converge to local maxima. The initial starting values needs to be precisely given to EM algorithm, because it is a bit sensitive to the starting values, but we can evade that by using the complete case analysis values or the available case analysis values as the initial estimates, and in most of the cases they work perfect. The rate of convergence can be slow, and generally the rate is inversely proportional to the amount of missing data. So, higher is the missing data, more is the rate of convergence. In general, the rate of convergence is linear, while for Newton-Raphson and Fisher's scoring algorithm, the convergence is quadratic. But the problem of Fisher scoring algorithm is that it requires the computation of second derivative. So, we see that EM has both advantages and disadvantages. Now, we would investigate some properties of the EM algorithm. Let us define Y observed as the observed data and Y miss as the missing data. Now, this Y miss can include random effects or latent variables. Let Y complete be the vector of Y observed and Y miss. The observed data likelihood we can write as F observed, which is Y observed, and theta, where theta is the set of parameters that needs to be estimated. So, the complete data likelihood is F complete, y observed, y miss, that is y complete, and theta. Now, note that if observed y observed theta, that is the observed data likelihood, can be obtained by integrating out the complete data likelihood over the missing data. So, in the E step, what do? We find a function q theta conditional on or given theta naught, where theta naught is the parametric value from the last iteration. So, example, for the t plus 1th iteration, theta naught is theta superscript t, and q theta given theta naught is expectation under theta naught, the log likelihood conditional on the observed values. Now, what do we do in the M step? We maximize q theta given theta naught with respect to theta to get the new estimates of theta naught. We put again the new estimates of theta naught in the E step and again do this M step until and unless we converge to a value of theta. So, the maximization requires the derivative or the partial derivatives with respect to theta of the log likelihood, which is here represented by L observed of theta, and this is nothing but the partial derivative with respect to theta of the logarithm of integral the complete data likelihood integrated with respect to the missing data. And by simple algebra, we can write this as integral of the derivative with respect to theta of the complete data likelihood and integrated with respect to the missing values or y miss by the likelihood for the observed data. Now, we can rewrite this by as a ratio of two quantities. The first quantity is the integral of the derivative with respect to theta by the complete likelihood into the complete likelihood by the observed likelihood. Now, if we do that, we can see that the first term reduces to derivative of the log likelihood of the complete data or log likelihood of theta, and the second term, if we see the second term can be thought of as the joint density of y observed y miss divided by the marginal density of y observed. So, this comes out to be the likelihood or the density of y missing conditional on y observed and theta, and this entirely is being integrated out with respect to the missing value, which in turn can be written as expectation under theta del theta of log likelihood of the complete observations of theta conditional on y observed. So, we can say that the score function of the observed data. So, we started with the score function of the observed data, which is del theta of L observed theta, is equal to expectation of score function of the complete data likelihood conditional on the observed data. Now, note that expectation under theta, the score function for the conditional score function is what I would say of the complete data likelihood given the observed data is del theta of q theta given theta naught at theta naught equal to theta. So, using these relationships, it can be shown that if the EM converges, it converges to a solution of the score equation based on the observed data. And suppose we assume that the EM converges to the value theta hat, then q theta given theta hat is maximum of theta hat. So, that means del theta of q theta given theta hat at theta hat is 0, that is del theta of the log likelihood of the observed values at theta hat is 0. So, a stationary point of the EM algorithm theta hat is a solution to the observed data score equations. Further, it is also possible to show that at each iteration, if theta 1 is such that q theta 1 given theta naught is greater than q theta naught given theta naught, then the log likelihood of the observed data at theta 1 is greater than the log likelihood of observed data at theta naught. That is, at each iteration the log likelihood is increasing. Now, to prove that, let us write the log likelihood of the observed value of theta is q theta given theta naught minus h theta given theta naught, where h theta given theta naught is expectation under theta log of the likelihood of the complete data divided by the likelihood of the observed data conditional on the observed data. Now, since log is a convex function, we can use the Jensens inequality, and using the Jensens inequality we can prove that minus h of theta given theta naught plus h of theta naught given theta naught comes out to be is greater than equal to minus log the log likelihood of the complete observations by the likelihood of the complete observations, which is equal to 0. That is, we can say that h theta given theta naught is less than equal to h theta naught given theta naught. That is, if q theta 1 given theta naught is greater than equal to q theta naught given theta naught, then log likelihood of the observed at theta 1 is more than the log likelihood of the observed greater than equal to likelihood of the observed at theta naught. In this session, we have learnt about few properties of the EM algorithm, and one of the most fundamental properties that we have learnt is that at every iteration of the EM algorithm, the log likelihood is increasing. Because the log likelihood is increasing at every iteration, EM becomes a very popular method for estimating the parameters in context to a missing data problem. Although we are saying here missing data problem, EM becomes a very important tool for estimating the parameters in problems where apparently there is no data missing, but there are random effects or there are mixture parameters, so which one cannot see in general and can be treated as a missing object. In the next session, we would use the data called faithful in R. So, this data set is about eruptions of geysers and comes in R by default in the data set package, and which shows a typical mixture distribution. So, here in this context we would see how one can use an EM algorithm and see what are the values. One thing that needs to be noted is that EM is a bit sensitive in terms of the initial values, because there is a tendency that the algorithm might converge at local maximas. So, we would investigate all these properties of the EM algorithm in the next session, where we would be analyzing completely the old faithful geyser data set, which comes in